we've seen what the forward stage model is, and we've seen that it all depends on input and output and saving information, and it's all down to zeros and ones. So what we're going to investigate in this section is what are these bits and bytes and zeros and ones, and how do they work and make the computer work. So we're going to look at the interaction of humans and technology. We're going to talk about what bits are, what bytes are. We're going to look at things like storage size. We're going to look at the binary system. For you who haven't done anything in mathematics for a while, just a quick introduction. And how many combinations does one byte have, and why do we have bytes? Then we're going to look at coding that information. We're going to look at the ASCII table. We're going to talk about file and storage space. And then we're going to talk about the new standard, which is Unicode. So first of all, how do we respond with a computer? Well, you've got to remember that all it is an electronic machine, an automatic electronic machine. And just like our light switch goes on and off, so do our computers. The only thing is, there are lots of these on and off switches. Millions, trillions. And the whole of the world at the moment lives on the standard of zeros and ones, especially with the internet. Every day, countless of trillions of zeros and ones are being fed backwards and forwards on the internet and through applications, and it all comes down to a simple switch. Now, when we switch a power off, power on, and then it will react, and actually, while it's on, it will do certain things, and it will feed our zeros and ones through. And all of these zeros and ones make a difference and make that computer run. And that's what it's all about. And the fact there are so many of them is what makes them so important. And not only are there so many of them, but the speed at which these things are processed. So whenever you think machines are intelligent, think again. All of these are based on zeros and ones, on and off switches that go on and off in repeating patterns over and over again. So let's explore these zeros and ones. We actually call them binary digits, bits, binary digits. We take the B from binary and the ITS from the end, and we call it bits. And one bit represents a logical state, one of two values. So our light bulbs aren't that intelligent because all they know how to do is go on and off. But that bit is the smallest unit of storage, and it can only be a 1 or a 0. You don't have much choice with 1 and 0. It's either this or that. So how do we put them together then to make some sort of meaningful sense? Well, we join them together. So instead of reading them one at a time, we read them in groups of 8. And this is what we call bytes. So a byte is a collection of 8 bits and commonly known as a computer word, although some people refer to 16 bits as a computer word. They used to in the old days. So when we say a word, it means that we can put them together, these 8 bits, into something that's a little bit more meaningful. So a byte is a collection of 8 bits and a combination of either 1s or 0. So how many of these can we put together? Okay, how many combinations of bits can we have in a byte? Well, in order to understand that, we have to look at something called binary, because that's really where the magic happens. So what is binary? Well, binary is a counting system that's based on zeros and ones. And what we're going to have a look at is how this 8 bits come together to give us a possibility of 256 different combinations. It's a little bit like having an alphabet with just the letters A and B in it. You can't make very many words out of those, but when you string all those letters together, you begin to make words. And that's the same with our byte. When we string these zeros and ones together, they begin to make something a little bit more meaningful, i.e. a choice from 0 to 256. But how do we know it's got 256 different combinations without actually sitting there and counting every single combination? Well, let's have a look. We're going to look now at how to create numbers using binary system. Now, we're all used to counting in the decimal system, and decimal system means we have 10 digits to work with. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we don't have any more digits. So what do? We don't start inventing new digits. No, we start putting them together. But what it means is, if I put a 1 now, the 1 moves across to another column, which we call the tens column, and we put a 0, which gives us 10. And then we continue using those same 10 digits all the way until we get to 99. And then we say, oh, we have no more digits. So we move the 1 across into the hundreds column. And then we start again, 100 all the way to 1,000, then to 10,000, then to 100,000. Get the idea? Well, it's exactly the same with binary. We only have the 2 digits to work from. So if we have a look at what we have here, instead of going up in tens, now we're going to go up in 2s. So we know if my digit is 0, then it's the same as saying 0 in a decimal system. If I have a 1, well, it's the same as saying 1 in a decimal system. But then I've got a problem because I've run out of digits. So what do? Well, I shift my 1 across into the next column, and because I've done 0 and 1, it must be 2. So we put a 1 in the 2's column and a 0 in the units column. Now we have 2. And so to make up 3, we add a 1 in the units column. So now we have 2 and a 1 that makes 3. But we've run out again. We have no more digits. What do? Surprise, surprise. We move the 1 over into the next column. So we now have a 4. Okay, because 3 was before, now we have 4. And then if we do 5, we put 1 in the units column. And if we want 6, we put another 1 in the 2's column. So we have a 1 in the 4's column, we have a 1 in the 2's column, and nothing in the units, which gives us 6. And then to make 7, we add 1 to the units. But there we go again, we've run out of digits. So what do? We move to the next column. So now, this digit in this column is worth 8. And so on and so forth, and we continue. Now, if we have a look at a byte where we've actually got 8 zeros and 1s in different places, well, let's have a look, because if we continue the sequence, you might see there's a little bit of a pattern there. It starts off with units, 2s, 4s, 8. What's the next one? 16, 32, 64, 128. And there's our 8 positions. Okay, now if we fill all those 8 positions, okay, let's go through the counting system and we fill all those 8 positions. Well, if you have a look, if we have a 1 in the furthest column, it means we have 128. And if we start filling in all the other columns, 1 in the 64 column, 1 in the 32 column, 1 in the 16 column, 1 in the 8, 1 in the 4, 1 in the 2 and 1 in the 1, these add up to 255. But you say, wait a minute, didn't you say 256? Yes, of course, because we also count 0, 0, 0, 0, 0, 0, 0, 0, 0, which gives us 0. Okay, so 256 different combinations. 8 bits, 1 byte has 256 different combinations. And you can see that from the screen and how we've worked that out. So, okay, why is that more important? Well, it means now that we can have different representation of these bytes to mean different things. How does that work? Well, if we have a look at our bytes again, which are 8 bits, those bytes, as we said before, are a computer word. And it's something that a computer is programmed to understand. How do I do that? Well, if you have a look at the example on the screen, that 1 byte there can represent a capital A. And the one below will represent a lowercase a. And this was something called the ASCII standard. And it was a way of coding or giving some sort of code that everybody could use and understand what was in there. And we'll talk about the ASCII standard a little bit later on. But now we can also think about these bytes to refer to how much memory we have. And you've probably heard, people talking about, kilobytes, megabytes, gigabytes, and now we're moving on to terabytes. So what are they? Well, we know that 8 bits makes 1 byte, okay? And we know that that would stand for 1 character. And we'll see how this develops, because if we have 1 kilobyte, well, a kilobyte is 1,000 bytes. Well, actually, it's just over 1,024. Why? Because it's binary. And 1 kilobyte, if you look at how many characters, can deal with 1,024 characters. Now, if we take this a step further, 1 megabyte equals 1,000 kilobytes? Well, 1024, but you get the idea. And 1 megabyte will allow us to have over 1 million characters, according to what we've spoken about before. And then it goes on. 1024 megabytes gives us a gigabyte. And look at that, we have something like more than 1,000 million characters that can be represented. And that's when we store things on a machine. And then we go from the gigabyte to next is a terabyte, which actually has 1,000 gigabytes. And you can see that for us, it's almost limitless characters. So you can get an idea of the size of our computer storage or our RAM, how much information we can actually hold in the computer itself. So all applications and data is measured in bytes, megabytes, gigabytes, now terabytes, and it will go on to petabytes later on because you can guarantee things will get bigger. So 1 petabyte will be 1024 terabytes. We'll stop for there because there'll be times when it goes bigger, but we'll see. Now I remember the first computer that I started playing around in 1981-82, which was a Sinclair Spectrum, had the massive storage of 16 kilobytes. Couldn't do very much. Now we're talking about terabytes. So you can see in 40 years, 35 years, how much we've actually increased the space and how things have increased, and they will continue increasing. The next one's exabytes, and well, maybe I'll see that in my lifetime. Probably, we'll see. So now let's go back to ASCII. We know that we can encode characters, and the ASCII standard was something that came very early on, and it's called the American Standard Code for Information Interchange. And it was a standard so that everybody who was using computers and writing code for computers had a particular standard to base it on. The only trouble is it's not very big, and it was a character encoding standard for any sort of electronic communications we were having. So as we saw before, the character capital A is a 65th encoded character in the ASCII table, and it's got an equivalent of byte, which is 0100000001. So that's our ASCII. And if you have a look, there is an ASCII table here, and you can see the capital letter A. And you can see that all the capital letters, all the lowercase letters and numbers are encoded. So they all had a standard code to be used. So whenever I wanted to display one of these characters, all I have to do is give the program its particular code, and it will give me that character representation. So take a look at the word computer and look at storage when you're using a word processor. The word computer equals 8 bytes. Why? Because it's got 8 characters in it. And you'll have a look that each one of those characters has an encoding. So a word computer to store on my text editor, that will take 8 bytes. Okay? So therefore, if you think that we have 500 words on average per page, and if we think that every word has on average 4 characters, then we can assume that 500 times 4 is how many characters we're going to have on the page, which equals 2,000 bytes or 2 kilobytes. So pretty much every page of text that we do will hold something like 2 kilobytes. Now, of course, that doesn't include things like, whether it's bold or whether it's in italics or any colors that we use or any other bits that the word processor might include. But you can assume that it's going to be around about 2 kilobytes. So now you understand size and how it's used. And as we look on the screen here, you can see that 2 kilobytes is something like 2,000 bytes one page. 1 megabyte will give us 500 pages. A gigabyte gives us 500,000 pages, which is probably about too much for me anyway. A terabyte will give me 500 million pages. A petabyte will give me 500 billion pages. And an exabyte will give me 500 trillion pages. So even the most avid writers of you out there are never going to fill up a space of exabyte, possibly not even to a terabyte. However, one of the problems that we had was that, of course, the ASCII code dealt with English characters. And so we had to have lots of different sets for ASCII to represent other characters. So we actually came up with a different type of standard. In the late 80s, there was an issue with the ASCII table because it was just designed for the English language. So to resolve this, they came up with a new standard called Unicode with the most common standard UTF-8. So any of our characters and so many other characters are used as standard UTF-8, and there's more than one UTF standard because obviously there are so many different languages and characters that we want to put in if you look at all the languages that are used in the world. So we came up with Unicode, and basically it's a standard for encoding characters worldwide, and it's got 6 different formats. And this is what's used in 95% of the websites across the World Wide Web. So we have all these different types of standards, and depending which particular standard or which particular language we're using and what particular characters we're using, we can actually use one of these. And it starts from UTF-1, UTF-7, etc, etc. So you can see that we now have a new standard that will actually cover pretty much all the different characters that you can think about. Now, ASCII itself had 128 characters. UTF has something like 2,147,483,648 different characters. That's just the one UTF. I think we've got enough there. Now, ASCII only handled the English alphabet, a minimal amount of other characters, whereas with UTF we can cover all the natural languages and many non-spoken languages as well, such as mathematical symbols and musical notation. ASCII only used 7 bits to store a character, okay? Whereas our Unicode actually uses 32 bits to store a character, or 4 bytes. So we have a much bigger range, and that's why it became the new standard, because hey, it's not only people who speak English or write in English that use computers. So UTF can still send information to computers that only use ASCII standard. Why? Because we still use the same coding for the basic ASCII characters that we've already created. So if the character for ASCII capital A was 01000001, and it's still the same in UTF. 1 byte still gives us that ASCII standard, and we can have a look at the spade symbol and how many bytes that occupies and the standard that it's got. So we still use the old byte formation even though we're using UTF-8 because that makes it backwardly compatible. So we've looked at how we measure size of memory and how we store our characters. We've looked at how we represent characters within a computer. But you know, binary is used for a little bit more than that, because it can also code computer instructions. It can represent an instruction to a processor, and a sequence of those will represent certain instructions that a processor will use. But we're going to talk about that a little bit later on. So we've now looked at what binary is and why we use binary and how that's used in computing in terms of size. We haven't spoken yet about how we use it for commands, but that comes a little bit later on.